I would like to discuss the results of our recent research concerning the application of the assembly theory to binary messages or bit strings. In fact, it's applicable to any strings, not only binary strings. I would like to start with saying something about the simulation hypothesis, because I'm not an ardent supporter of this hypothesis. However, it does, why I'm not, because it doesn't answer the question about the nature of the simulator, but it does, otherwise it's correct by focusing on information rather than on matter. And twice it establishes something that I would call a common now, like a common present moment for every living observer, which is, according to simulation hypothesis, for whom the reality is simulated. But without such a common now, we would, for example, we were considered as clocks, as mechanical clocks, as Albert Einstein theories and other black universe theories predict, then we would inevitably desynchronize, and our communication wouldn't be possible. So the importance of such common now for everyone is important. I believe that we should go deeper into the nature of reality, and that's what the assembly theory does. Object is defined in this theory not as a set of particles in space, but rather by the history of its formation. It introduces the notion of an assembly pool. It contains the basic units, be it chemical bonds, be it bits, like in our case, and the subunits that were previously assembled. And then we have the assembly index, which is the smallest number of steps required to assemble an object from these basic units and previously assembled blocks. And the obvious consequence, which is obvious, which were not obvious. I mean, I would like to say something as a patent attorney, because as a patent attorney, I know that every invention is in fact an improvement of some former invention, and which is known as the state of art. And there is something called unobviousness. And many times I've had this moment when inventor explained his invention that after hearing this about this invention, I was thinking to myself, well, that's obvious, but it wasn't obvious before I heard it. So it's obvious to me now that the presence of many copies of the same object is a clear indication that a selection took place during the assembly of this object. But this selection could be biological, technological, any possible. So this is just a drawing I've taken from Lee Cronin's team paper published in Nature. Its title is Assembly Theory Explains and Quantifies Selection and Evolution. The assembly theory was developed beginning with 2017 by Professor Cronin and his team from Glasgow. So as you can see, there are two examples. The first one concerns the chemical compound, and basic blocks are chemical bonds. So each joining two bonds to form another subunit is considered as a step. Perhaps the easiest way to explain would be the third example, where the building blocks are the simple hexagonal patterns. So as we see, up to the third step, only the basic building blocks are used. But in the fourth step, we use the subunit that we used after the second step. And in the fifth step, we use the subunit we made in 4 steps, and so on. Now, we use the theory to analyze the bit strings. So consider, for example, these 2 bit strings. They have the same Hamming weight, meaning that the number of ones is the same. And consequently, they will have the same Shannon entropy. It will be entropy equal to 1 in bits, because there is the same number of zeros and ones, 4 zeros and 4 ones. However, the assembly indices of these bit strings are different. For example, to assemble the string, first one, we first assemble 0 and 1. Then we use the 0 and 1 that we assembled. We take it from the assembly pool to assemble 0, 1, 0, 1. And in the final third step, we assemble this 0, 1, 0, 1 that we've already assembled with the 0, 1, 0, 1 that is in this assembly pool. So the assembly index of this string is 3. Meanwhile, the assembly index of this bit string is 6. So the bit string having lengths being the subsequent powers of 2, 4, 8, 16, 32, and so on, will have assembly indices corresponding to these powers. These are these points on this graph. This red line is the lower assembly bound on the bit string assembly index, and this curve, which is logarithm with the base of 2, is something which is called the general assembly bound. So as we see for lengths 8, 16, these bounds correspond to each other. So the second string, we need 6 steps to assemble it because there is only one pattern that can be reused, namely 0, 1. So as we can see, the assembly index is bounded. First, and the lower bound, the red bound, is general. I mean, it is universal for any string, not only bit string. Regardless of the number of the radix, of the number of the alphabet symbols in this alphabet, the lower bound would be always the same. The upper bound is n-1, as it's clearly visible that to assemble a string having 4 bits, we can assemble it in 2 steps, in case it is 0, 1, 0, 1, or 3 steps, in case it will be 0, 0, 0, 1, for example. But at some point, and it happened turned to be 6, it occurs. We are in the situation when there are patterns that we can reuse. That is why this upper bound is no longer n-1 when n is the length of the string, but something lower. Obviously, for larger number of the symbols available than 2, the upper bound would separate from this n-1 curve anyway. This is striking that for up to 3 bits, the assembly index is unique, and the first differentiation is at the level of 4. It turns out that 4 bits is the unit of a black hole entropy, Bekenstein-Hawking entropy, because there is something called information capacity of a black hole, which is nothing like the number of Planck areas on the sphere. But we'll get back to it later. So as we see, there are gaps between the logarithm with the base of 2 and this general bound, which in fact is the shortest addition chain. This is the shortest addition chain, the concept known from mathematics, which is at least NP complete to calculate. So we have defined, motivated by the assembly equation of the assembly theory, an equation to capture these gaps. And we call it the degree of causation. Why? Because while assembling the string of length being the subsequent power of 2, the assembly path is unique, but the other strings are can be constructed differently, leaving different subunits in the assembly point, depending on the way that we choose. And certain patterns were revealed here in this when we define this equation. So firstly, strings being the subsequent power of 2 have a degree of causation equal to 1 because they can be assembled in only one way. Then we have strings which are the sums of the powers of 2, and these are those strings here. And the minimum degree of causation for the strings is half 1 divided by 2. On the other hand, for numbers which are not the powers, the sums of the powers of 2, the degree of causation is lower than half, and the maximum value here is not half as we would have expected, but 15 divided by 32. Furthermore, there are some patterns, some general patterns in the strings. However, we are not sure if this is the problem that, I mean, I am convinced that there is more exception than, for example, this one, for a number in the form 2 to the power of s plus 3 to the power of 3 multiplied by 2 to the power of l, for l within this range, we will have the assembly index equal to s plus 2. And similarly for this range. And perhaps there are more regularities to be discovered, but still, this is a subject that only we touched in our research, so certainly it requires further research. Then we consider something I call binputation, namely if we have basic symbols in the assembly pool, 0 and 1, then we can define only 2 commands for a binary program. And the first would be to take the last element from the assembly pool, join it with itself and output, and the other would be take the last 2 elements from the pool. So the zero command will create the assembly index, the string 0, 0, because it turned out that the pool starting with 1 is required for some thermodynamical reasons. So our basic pool is not 0, 1, but 1, 0. So the program 0 will assemble string 0, 0, and so on. And it turned out that these programs have quite interesting properties, namely 6-bit programs like these ones. Each one of them has 6 bits, and star is a placeholder for 0 and 1. Similarly, the other star. So star here can be 0 and 1. In this case, it corresponds to this string. So as we see, the 6-bit program starting with any symbol, then 0, then any symbol, produces bit strings in the form the first any symbol 0, so star 0, star 0, star 0, and produces the string of length 64, which is the string having the assembly index equal to 6. Furthermore, string with this length of 21 bits in this form has an assembly index also equal to 6. However, there are some exceptions. For example, this is exception 32, because the assembly string of a string of length 32 is 5, not 6. And here we have a double exception, because if the star is 4, then we have a situation when we have assembled string of length 32 in 6 steps, but we can assemble the strings in 5 steps. So this program is not elegant. An elegant program is a concept that was introduced by Gregory Chaitin, and the elegant program is the shortest program capable of providing a given output. So furthermore, the elegant program cannot find an elegant program. No program shorter than an elegant program could find an elegant program. This is a fascinating subject, and it was very well researched by Gregory Chaitin within the context of uncomputability. So it turned out that the subsequent strings, the strings generated by the program defined like this, have lengths that can be expressed as product of Fibonacci numbers, and revealed a golden ratio also. So this is also a matter that we have only briefly touched, because we could consider, for example, the alphabet of 3 symbols, and then the situation would be different. But anyway, these results are intriguing. So this is the same plot that we've seen previously, but now the blue dots show the assembly indices of the strings that were created by this trivial program with only two commands, 0 and 1. As we can see, they produce not only strings having the minimum assembly index, namely the shortest addition chain for n, but also string with larger assembly indices. So this is a plot I would like, I must give credit to Professor Watson because it's his discovery. But I kind of, I was curious if it's true. So I have made this calculation myself and they are 100% correct. Namely, Dr. Watson compared the genotype of a COVID virus starting from the outbreak of the epidemic and more than 2 years later in Egypt. And it turned out this genotype contains 2993 nucleobases. And it turned out that the number of mutations were almost linearly increasing. At the same time, the Shannon entropy was almost linearly decreasing, which means that these strings, these genotypes, were becoming less balanced. So the number, if they were converted into binary strings, this string would have, I mean, there would be more zeros than ones as time goes on, or vice versa, which clearly says that the information is evolving. And it's not that the genotype of the COVID virus, of any virus for that matter, is a lie but its assembly process or its evolution indicates the evolution of information. This is the fact of nature. So we were thinking what could be as a part of a greater our larger research into emergent dimensionality. We have tried to define the structure of information capable of assembling the information, starting with a dissipative structure. And I will, in our opinion, the dissipative structures are structures of nature that don't have a memory, but they're capable of assembling carrying the information starting from 3 bits. Then we have a biological cell, a structure provided with memory. If assembly theory captures selection of evolution, then selection is nothing but choice. And the notion of choice requires time. Choices are made in time. Multicellular organism would be a set of cooperating cells, all smaller multicellular organisms, and also provided with memory. Then we have a human, which is nothing, in our opinion, nothing like a multicellular organism, capable of using an abstract modality-independent language. And dissipative structure, I believe, provides these the structures with non-computability. This is the notion also introduced to science by Gregory Chaitin. And by very definition, artificial intelligence has no access to non-computability because they are Turing machines and they can only operate in bits, which also brings an interesting question of these curves being continuous, not discrete. Of course, it's hard to say what is the length of p-bit string, namely a string containing 3 bits plus the fractional part of 14135, and so on. But I believe that if fractional dimensions were experimentally confirmed, that perhaps this is something worth considering. So we have then tried to speculate about the evolution of the universe starting from the Big Bang, that is from first bit. And we are in the opinion that the upper bound on the assembly index indicates that up to a certain moment, up to the onset of life, the evolution of the information of the in the universe within the period that we describe as 10 billion years between the Big Bang and the onset of life was in fact timeless evolution, timeless and choiceless. The entire space was explored and all that could be assembled was assembled. But with the onset of the upper bound, we are in a situation where even the most patternless, the most sophisticated string can be assembled in a simpler way, which kind of provides two paths of evolution. The first is assembling a string longer than known before. These are the slanted lines. And the second one is, of course, if this new string of the longer length is assembled, it is most likely it will be suboptimally assembled. And we observe this phenomenon in our life. For example, the invention of plane. The first plane was certainly suboptimal, the first plane made by Wright brothers. But as soon as it is shown that some novel information is possible, then nature seeks to optimize its assembly pathway to reach the assembly index. So in our opinion, there is a certain threshold of assembly index in terms of that is available to a living dissipative structure, namely to a life, non-human life. We contemplate that they are capable of assembling structures below this threshold in a larger number of steps, providing that this number can be optimized to the level below this threshold. In this first example, when we consider the strings of 8 bits that having an assembly index of 6, it can obviously be assembled in 7 steps, but in this case, we wouldn't be using the assembly pool. And if the assembly pool is something that kind of contains the information previously assembled. So this is the idea that is the result of the known theorems of the orthogonalization interval. The first one was developed in 1944, and it says that the quantum system having the energy standard deviation delta E requires time delta T to get from one state to the other orthogonal state. And the lowest such period is known as the orthogonalization interval. So the product of the standard deviation of energy and this orthogonalization interval must be larger or equal than p h bar divided by 2. This is closely related to the uncertainty principle, and the difference is the factor of 2. So this is somehow an uncertainty principle multiplied by pi. The similar theorem was discovered in 1998. This time it relates to the average energy of the quantum system. What else? From our previous research, we know that the Bekenstein-Hawking entropy of a black hole equals the number of bits of this black hole, number of Planck areas divided by 4. That's why 4 bits of the black holes provide 1 unit of entropy. We also found out that for any holographic sphere, the number of the entropy of such a sphere is n1, which is the coming way, the number of ones divided by 2. By simple equating these two equations, we found out that in the case of black hole, the n1 is equals half of this the bits available at the black hole, which means that the black hole can be considered a balanced binary string that has a natural Shannon entropy, unit Shannon entropy, because I'm sorry. Okay. Am I being heard, Melvin? Hello?
Yeah, you are good.
Okay, sorry, because some other program I made an interruption. So, furthermore, it was established by in a set of terms in 2009 that that these bounds become equalities if the quantum system is the qubit, which is quite peculiar, of the zero energy state and E1 energy state. And it was further established in 2009 that there is another bound like this time for the maximum energy of the system. And this bound turns into equality if the qubit has this particular form, where Emax is the maximum energy. So this indicates that the only natural quantum system that attains these three bounds is a black hole. And well, this is the result of this of these calculations, this sphere. We call it a entropy variation sphere or dissipative assemble. I believe that this is this object that assembles this information. So these bounds can be expressed like this. The first one is a black hole with Emax, maximum energy of the system, the black hole energy provided by the mass energy equivalence is also equal to the E1 energy agent state, and average energy equals the energy standard deviation, and these are the intermediate positions of this sphere, which has something which is given by this I mean, this is the result of the fact that I don't have this equation here, that the average energy of the system must be larger than maximum energy divided by 4 and lower than maximum energy divided by 2. So maybe as at the end, if we consider the dimensionality of space as a complex number, and I'm convinced that dimensionality of space is a complex number with 3 spatial real dimension and imaginary time, because the only real imaginary number is I multiplied by 0. So the reality we present is in fact 3-dimensional because we always perceive it now, and now is the 0. But in general case, the equation for the surface of the ball in imaginary dimensions is a complex number. And this complex number, interestingly, contains a trigonometric term that vanishes for the radius equal to 1 divided by square root of pi. And precisely this is the radius that gives the 1 unit of the Bekenstein-Hawking entropy. Of course, with the without the Boltzmann constant, we should divide it all by the Boltzmann constant, because otherwise the entropy is dimensionless. So that clearly means that the spherical object, say an apple, is spherical only when we look at it, and it's no longer spherical 5 minutes later or 5 minutes before. So this is we are quite aware that these results are quite, as my partner who co-wrote the paper with me, Wawrzyniec, says, it's esoteric. It is esoteric, of course, but we believe that it may find it will find a real application. For example, axis of evil is one of the potential applications of this result. This is a strange correlation of the plane of the solar system with the observed microwave background radiation. There is clearly infinite number of orientations of the plane of the solar system. So why this particular one was chosen by nature? Another example would be quantum Hall effect with these strange plateaus and or ball lightning, another physical unexplained phenomenon. Perhaps also sonoluminescence, also another interesting phenomenon in which bubbles containing vapor suddenly collapse, emitting light. And there are results suggesting that this light emission is Bekenstein-Hawking radiations, meaning that those bubbles turn into a small black holes, and they evaporate by emitting a black hole, Bekenstein-Hawking radiation. Other possible result would be the data analysis of the gravitational events and other observations that are being collected while we talk by Light Bridge and other instruments. I'm convinced that the reality that we experience does not exist observer independently, which was established by Czesław Bruckner in his famous no-go theorem for observer-independent facts. Thank you. I have some more slides, but they are in a way unrelated. So perhaps I would finish now, or I don't know. Melvin?
Simon, it's entirely up to you. We are just over half an hour through your presentation. If you have more slides and you want to continue, I think you should.
Okay. So other research that remain concerned, for example, the application of a novel recurrence relation that helped us to establish the values of the volume on the surface of balls in negative dimensions. By removing the singularity, because the gamma function is undefined from non-positive integers, -5, -4, and 0. But we've shown that for negative even dimension, it is volumes on surface are 0, but it is not the case in negative odd dimensions. And they are clearly defined. So we remove the singularity, showing that volumes on surface of balls in complex dimensions are holomorphic functions, which means that they are well defined. We have also analyzed the surface and volumes of simplices, like triangle is a simplex in 2 dimension, and orthoplices and cubes. Basically, those are the only convex polytopes that are present in all dimensionalities. In 2 dimensions, we have an infinite number of regular features. In 3 dimensions, we have 5 solids, regular solids known as platonic solids. In 4 dimensions, we have 6 such regular polytopes. But in any other dimension, like 5th, 6th, 11th, and so on, there are only 3, namely simplices, orthoplices, and cubes. Orthoplices are dual to cubes. And it turned out that in negative dimension, for example, the surfaces of simplices turned out to be purely imaginary. But for the orthoplices, it turned out that their volumes are real, while their surfaces are imaginary. these nice glasses were also reviewed. I think this is as kind of a reflection relations that we define. And SCB denotes that this is the simplex circumscribed in ball. And for example, this is cube. CIB means it's a cube inscribed in ball. That's how the volume of such a structure looks like in a real dimension. It's also complex. Impressed by Dr. Hobson's research, I also tried to find. I mean, there's nothing new. There's simply a replication of Dr. Hobson's research on the entropy of chemical elements, namely the Hans rule, which says that, for example, on p orbital that can carry at most 6 electrons, the Hand rule states that the preferred are those configurations with the maximum amount of unpaired electrons. But nature also selects this electron configuration that minimize Shannon entropy. So a natural extension was to use this rule to calculate the entropy of all chemical elements by summing the orbital entropies of the electron configurations. And it turned out there are no element violates the Hund's rule, but there are about 20 elements violating the Aufbau rule. The most remarkable is palladium. However, it turned out that even those Aufbau violators that have different configuration as measured in experiment than the one provided by the Aufbau rules still have the same entropy. Yes, and this is perhaps the first research I made in 2018. It was an analysis of the extended Wigner's friend experiment. This experiment says that an experimenter considered in a closed laboratory is performing an experiment, and depending on the results of this experiment, is preparing a quantum state, which, he then delivers the results of his quantum measurement to the second experimenter, also enclosed, contained in an enclosed laboratory. And the second experimenter prepares quantum states according to 2 different scenarios. So it's clear that if heads were revealed as a result of the coin toss, then we'll have the state H0, heads and 0 will be possible. If tail, we have tails and 0 possible, but also tails and 1, but there is no state heads and 1 because it's impossible to produce. And such a quantum states contained based on these 2 qubits being measured by the other 2 experimenters led to a contradiction. But the point is that we cannot consider there is no unitary transformation that can transform these pure states and the other quantum states, which is has 2 non-orthogonal versions, into such a state which invalidates this experiment. It simply says that we cannot model quantum states contained. The first experiment, perhaps known to the world, is the Schrödinger cat, in which the quantum states is entangled with the cat, and we then wonder if the cat is dead or alive, and so on. But the whole point is that we cannot even consider a cat as an enclosed container, because not only quantum mathematics is non-local, everything is non-local. I think we should finally call quantum theory quantum mathematics, because this is a part of mathematics. And the fact that Bell's theorem proved mathematically in 1964 was the Nobel Prize of Physics was given for the experimental confirmation of a mathematical theorem. So it's something I cannot comprehend. I mean, no one questions the mathematical proofs of mathematical theorems. Why was it the case of the Bell theorem? Yeah, perhaps I should have also mentioned the role of acceleration in the choice, because this is interesting that I believe that the acceleration, the inertial acceleration, is related to the notion of choice. As my friend once said, the acceleration is a necessary steady state preventer. Michael, thank you. And I believe this is true. Namely, gravity has only one direction, but you can choose the direction of acceleration, and this is I believe how those dissipative structure works by. Anyway, this is an ongoing research, and there is more questions than the answers we can provide. Thank you.